Hi, I'm Ralph Gable. Today I want to talk about three really weird numbers that you just can't escape when you're talking about electronics. Two of them are numbers that go on forever and ever and ever and ever. And one of them is just a completely impossible number. That's why it's called an imaginary number. That imaginary number is the square root of -1, and in the math world it's represented by the symbol I, and in the electronics world it's represented by the symbol J. I'll explain more why a little bit later. The next one is Eulers number. It is also referred to as the natural exponential, represented by the symbol E, a lowercase e. And the last one is one that most people are pretty familiar with, and that is pi, represented by the Greek letter pi. So now let's talk about this a little bit more. Well, the first one that we're going to cover is the square root of -1. Now, this number, this square root of -1, is the impossible number. And it is replete through mathematics and physics, including electronics. And in the mathematics world, they represent it with the lowercase I. And in the electronics world, they represent it with a lowercase j. And the reason for this difference is that in the electronics world, we reserve the lowercase I to represent current, whereas J now becomes the square root of -1 for us. And you say, well, why is the square root of -1 an impossible number? It is an impossible number because any number multiplied by itself is a positive number. So if we had -1 times -1, we're going to get +1. If we have -2 times -2, that's going to give us a +4. So this is -2 squared equals a +4. Now the operation of the square root is asking the question, what number do I multiply by itself to get the number in question? So if we say the square root of 4, what we're asking is, what number do I square, or what number times itself equals the number in question? Well, we've already seen that any number times any itself is always a positive number. So if we are asking the question, what number, when squared, is equal to -1, there is no answer to that question because any number multiplied by itself is always a positive number. So you're kind of stuck. So if we were to say the square root of 16, our calculators would report, and we would immediately say, well, that's 4, because 4 times 4 equals 16. Reality is the square root of 16 is plus or minus 4, because -4 times -4 is still plus 16. So this is the impossible number. And that's why it's referred to as the imaginary number. And when it's plotted, just as a side note here, we have real numbers that are plotted on the horizontal axis, and the imaginary numbers are plotted on the vertical axis. So now on to one of our ongoing numbers, Eulers number. The next one we're going to cover is Eulers number. Now you look at this and you say that, well, that says Eulers, but it's pronounced Eulers number. It was discovered by a mathematician by the name of Leonard Euler many eons ago. He was a protege of Bernoulli, and it is represented by the lowercase e, and is approximately equal to 2.718, and then you can continue the calculation out as many decimal places as you like, but you're never going to get to an end. It is at the heart of what we call the natural exponential and the natural logarithm. We'll get into that eventually, but the natural logarithm, you may have seen this terminology, ln, that is the natural logarithm, which is the logarithm to the base e. We'll talk about that in a little bit. Now, this number involves an awful lot of really incredible math, and it is used in electronics and physics and finance and all over the place. It is at the heart of these long series and calculus and all kinds of other funky things. You don't need to understand its origins and how it's derived and how it was discovered and all of that. Just know that this number, this E, this Eulers number, greatly simplifies some of the kind of calculations that you might have to do in electronics. And here's a really simple example. Let's consider a very simple example here. We have a battery, and we have a resistor, and we have a capacitor, and let's put a switch in here. So we have RC. Now, if we are interested in the voltage across the capacitor, and we want to know what the voltage across that capacitor is at any given time period. So in other words, we have time here, and we have voltage across the capacitor here, and time equals 0 is when we close the switch. We want to know what the voltage across that capacitor is at some time out here. Well, how do you calculate that? Now, if we were to go into all this, it ends up actually in some pretty funky calculus that you have to go through, integral equations and all kinds of other fun things. But Euler's number comes to the rescue, because you see, think of it now, the voltage across the capacitor is directly proportional to the amount of electrons that have been dumped into it, its charge. So we close the switch and electrons are traveling here into this capacitor, building up a negative charge on this side of the capacitor, making this side positive relative to this side. Now, if this current that we are putting into the capacitor, if this current were a nice linear entity and we were just, dribbling electrons in at a very specific rate, then we would see a nice linear increase in the voltage across the capacitor. The problem is that in this circuit, it's not linear. It's not a constant current. Because if we think about it, we'll call this V applied. Now, at time t equals 0, we are here. The voltage across the capacitor is 0. That means that if the voltage across this capacitor is 0, that means that the voltage across the resistor is the same as V applied, and the current through the resistor is equal to V applied over the resistance. But what happens? Charge gets shoved into the capacitor, and so at some new time along here somewheres, we have a different voltage across the capacitor. Now, the voltage across the resistor is V applied minus the voltage across the capacitor, which means that the current is now reduced. And so, as the capacitor charges, the current continues to decrease over time. And if the current decreases over time, then the charge rate, the amount of electrons going into the capacitor, is also changing over time, and the capacitor will have something that looks more like this. And that gets into these wonderful integral equations. Well, Eulers number to the rescue. So with Eulers number, we can write the following equation, which will help us greatly in our quest. The voltage across the capacitor at any time t is equal to the applied voltage times Eulers number brought to the power, 1 minus Eulers number brought to the power minus t over RC. So the voltage across the capacitor at any point in time t is equal to the applied voltage times this whole quantity here, 1 minus Eulers number, E, brought to the power minus t over RC. And now, this eliminates all of that funky calculus that we would have to do otherwise. A nice simple equation you can sit and do on your calculator without an issue. So that is how it helps us to get past some of the complicated stuff. And again, Eulers number is used all through physics and mathematics, and even goes into finance and all kinds of different places. And a little bit later, I will show how Euler's number, the square root of -1, j, and our next entity all are related to one another. That will be in the extra credit section. Well, our next magic number or weird number is something a lot more familiar to us. It's the number pi, 3.1415 on infinitum. It is represented by the lowercase Greek letter pi. It is equal to the circumference of the circle, the distance around the perimeter of a circle, divided by the diameter of the circle. And why is this important to us? Why is pi important to us? It's because it is at the heart of all this sine wave stuff that we need to be concerned with. And you say, well, how is pi and circles and all of that involved with sine waves? Well, let me demonstrate here. If I get rid of my line, and let's just imagine now we have a disk. This is a disk, and we have managed to very, very, very carefully attach a pencil to the very edge of that disk. And we have taken that whole thing and set it up so that the pencil is on our disk and touching a piece of paper or other material that it can write on. Now, we take this pencil and we begin rolling our disk along. And while we're rolling that disk along, we're very careful to keep the pencil in contact with the paper as it rolls along. Well, what kind of mark do you think you get on the paper? You get this lovely sine wave. So pi, because it's involved in this unit circle, is intimately involved in this whole sine wave stuff. And then we talk about trigonometry, sines and cosines and all that kind of good stuff. But that's why pi is important to us, and it does end up in the middle of some of our more important equations. I mean, consider this one. This is the equation up here for inductive reactance. So inductive reactance in ohms is equal to our impossible number J times 2 times pi times the frequency in cycles per second times the inductance of our inductor in henries. Now notice, if you will, we have this entity here, 2 pi f. If you were to look at the equation for capacitive reactance, you would find the same entity in there. Well, we keep seeing that entity over and over and over and over again. Well, let me introduce you to a new piece that is also all through everything, because, you know, we get tired of writing the same thing over and over again. Well, it turns out that if you have a circle, now we measure angles in degrees, so from here all the way around is 360 degrees, right? Now, we already know that if you were to take this circle and roll it along with our pencil on the edge, we would end up with a sine wave like this. And so from here to here is one cycle. It's 360 degrees. But it just so happens that there are 2 pi radians also in that 360 degrees. You'll see it abbreviated rad. And by the way, radians, if you ever do any work in Excel using their trigonomic functions, they want their angles in radians, not degrees. So this equation up here goes from this to inductive reactance in ohms equals the impossible number J times, and by the way, radians per second, 2 pi f is represented by the omega, J omega L. So we use F for cycles per second. We use omega for radians per second. And so it tends to tame our equation. So there you are with pi, another one of those forever numbers that you can't escape in electronics, and an introduction to the concept of radians and radians per second for frequency. So there you go. We have covered all of these really weird numbers that you can't avoid in electronics. We've covered the square root of -1, which is the impossible number represented in electronics with the symbol J. And we've covered Eulers number, which is one of those numbers that goes on forever and ever and ever. It's represented by the lowercase e and is approximately equal to 2.718. And we've covered pi, which is also another one of those numbers that goes on forever and ever and ever, 3.1415, represented by the lowercase Greek letter pi. And now we will go on to your extra credit portion. How are these 3 things connected together? So if you're interested in a little interesting math to follow, keep watching. If not, thanks for listening. Toodaloots. And now we've come to the extra credit portion of our video. And before we get into this, I need to do a quick, for some might be an introduction, for others as a reminder. The logarithm asks the question, if I have a base number, what power do I raise that number to in order to get the number in question? So let's say I have the log to the base 10 of 100. So we're asking the question, what number try again. We're asking the question, here's our base, what power do I put here in order to get 100? Well, we know that 10 times 10 equals 10 squared is the same as 100. So the answer to this question, log to the base 10 of 100, is equal to 2. So if we do the same thing again, log to the base 10 of 1,000, we know that 10 times 10 times 10 is the same thing as 10 to the third which is the same thing as 1,000. So log to the base 10 of 1,000 is equal to 3. Now, it doesn't always have to be to the base 10. You can have a logarithm to the base 2. You can have a logarithm to the base anything. The idea of the logarithm is just asking that question, what power do I take my base number to get the number in question? So, in the electronics world, and in math and finance and all kinds of physics and all that stuff, we have what's called the natural logarithm, which is log to the base Eulers number of whatever it is that we're looking for. And this, rather than having to write this, what they do instead is they go ln. And this stands for the natural logarithm. Natural logarithm. And it's just a shorthand way of writing this. All right, now that we have that established, we're going to answer the question, well, what relationship does the impossible number j have with Euler's number, E, have with pi? Well, it just so happens that the natural logarithm of -1 is equal to our impossible number times pi. Now this is remember, this is the same thing as the log to the base e. So we're saying is that the power that we bring e to get -1 is this. So that means if we were to take Euler's number and raise it to the j pi power, then that would give us -1. Or some people like to write this way, e to the j times pi plus 1 equals 0. Now you notice we have all three here. We have Euler's number, we have the impossible number, the square root of -1, and we have pi all in one equation. And so they are related to one another. And so there's your extra credit. How are all three of these really weird numbers associated with one another? Thanks for listening. Toodaloots.